Okay, very good morning to Professor Judith Irwin and good evening to all of you participants in this winter school. It's been a real pleasure for us to have Professor Judith Irwin speak to us this evening over here and morning in Canada on galaxies. Professor Irwin is Professor of Physics and Astronomy at Queen's University in Kingston, Ontario, Canada. Her research has largely been on spiral galaxies and particularly the ones which are seen edge-on. And these are systems, because they're seen edge-on, you can study the halo, the faint halos, which consists of gas, dust, and magnetic fields, as we shall hear about today. And she initiated and led this very exciting project called Change ES, which is started with an EVLA survey, which has produced a bulk of the results, but has since grown to use data across wavelengths to produce some of the most interesting results in our study of galaxies in recent times. And she's also written an excellent textbook called Astrophysics, Decoding the Cosmos, which is published by Wiley. The second edition came out this year. It should be available in the Ayuka library. I'd requested them to get a copy or two. And this is something which I've also used in teaching not only the MSc students, but also the Interdisciplinary School of Sciences. And they've all enjoyed what has been taken from the book. So it's a pleasure to have you with us, Judith. So could I invite you to talk to us? Thanks very much for making the time.
Thank you, Dr. Yeah, I appreciate it very much. I think very fondly of my time spent in Pune, and now it's at least a decade ago, more than that. Was wonderful experience for myself and my family. So it's a pleasure indeed to speak to you today. I'm going to give you a kind of overview of our changes results. So I hope that's satisfactory for you. Oops, I'll make sure I get this right. Okay. Yeah, so the winter school, right? Winter solstice is at 10:59 a.m. Eastern Standard Time. So that's a little less than 3 hours from now. So I guess I get to speak at about the nadir of the sun, which is kind of fun. Okay, I thought I would talk about this first image a little bit. This is actually a median of 30 galaxies. So what I did for this image is, first of all, you see the actual pretty picture was made by Jan English, and she put an optical image of NGC 5775 on top, but I made the median. And so what we have done here is taken all the galaxies that we looked at, rotated them so that their x-axis corresponds to the major axis, and then scaled them in angular size so that all the smaller galaxies are scaled up to the larger galaxies and then stacked them. So this is the result. And as you can see, there's a lot of emission coming from this stacked galaxy. And there's a lot of emission above and below the plane here. If you look at the spectral indices of the radio emission, as you go up and down, they are actually very steep. The spectral indices are steep, which means that we're looking at non-thermal emission, we're looking at synchrotron emission, and there are two ingredients to seeing synchrotron emission. The first is magnetic fields, and the second is cosmic rays. And if any one of those two things are missing, you don't see synchrotron emission. And so it means that we have magnetic fields extending far above the plane in a typical spiral galaxy. So we're saying, in fact, that radio halos are quite common in spiral galaxies. I'll talk about the Changes project. We are looking at 35 edge-on galaxies at L-band and C-band. So L-band is, for us, is 1.6 gigahertz, and C-band is 6 gigahertz. And we're looking at 3 different array configurations of a very large array, and 2 different array configurations at C-band. So altogether, we have 5 data sets at 2 different frequencies. So B array is the most spread out on the ground. So that would be looking at the smallest spatial scales in the sky. and D array is the most compact configuration on the ground, which looks at the largest. So that's very similar to the GMRT, in fact. We are looking at all four Stokes, and so looking in polarization, which tells us about the magnetic fields. We also have a bunch of the GBT data, the Green Bank telescope for the zero spacing flux, which I think you've either learned about or will in this summer, in this winter school. This part of the project has been delayed somewhat. First of all, because of the hardware. We did not have the back ends at the GBT, which could match the VLA for quite a long time. Those data have now been collected, and we also had some software issues. So we're still waiting for the final results of combining the two data sets. Now, the picture I'm showing you here of all these people, these are the original people involved in the consortium with all of our pre-pandemic hairdos here. And you can see a very important person as part of the project, Judith Irwin. So we have a really beautiful group in terms of knowledge about observing, knowledge about theory, X-ray information we have. So we have really combined a lot of information, as Dr. Saki has said, across the bands, and a lot of work actually still needs to be done in this regard. Okay, so for science, we wanted to look at these halos, and we needed to take a look at what we'd like to what we'd like to learn from all this. The image that you see on the right was actually taken from the GMRT, and I love to show it because you can see that NGC 3079, which is an optical image here. I hope you can see my pointer. And then there's this 615 megahertz radio data, which, as you can see, is hugely extended. And not only is it hugely extended, but it shows structure far, far away from the plane. So this is published some years ago. And this is a well-known galaxy that has two radio lobes coming from the AGN at the center. So we wanted to probe cosmic rays and magnetic fields at the interface between disks and halos, and polarization is quite unique to this survey so far. We wanted to see how frequent these halos were and what the physical conditions might be. We have this issue of lagging halos, which has been understood for some time, but the reason for it hasn't been understood. That means that as you go up in Z, height from the major axis, the velocity tends to lag behind what's going on in the disk. Cosmic ray transport and wind speed, a lot has been done on that in this group. If you look at the magnetic field, the synchrotron emission tells you the magnetic field, which is perpendicular to your line of sight, in other words, in the plane of the sky. But Faraday rotation tells you about the magnetic field along the line of sight. And so if you can work hard and put all this together, you can get some information about the three-dimensional structure of the magnetic field. AGNs was not a major part of the project, but it turned out to be quite interesting in the end. I'm not saying too much about that today, but I can comment a little bit later if you wish. Whoops, something happened. Oh, okay. Okay, there was a technical impetus for the study, and that was really that, a decade ago or so, the VLA had undergone an upgrade of going to wide bands. And so that allowed for multi-frequency synthesis, which we have done in our study. In-band spectral indices could be quite interesting, and rotation measure synthesis, of which more soon. Now, what was our galaxy list? What was the criterion? What were the criteria? First of all, we just went to the Nearby Galaxies catalog. We looked at galaxies that have inclinations of greater than 75 degrees. The inclinations were not necessarily known perfectly in this catalog, but we did this anyway, just to give us a starting point. We wanted a scale of 4 to 15 arc minutes And that was just to match the scales to the available arrays for the VLA. We wanted to make sure that the declination was high enough to observe it. And we picked an L-band flux greater than 23 millijanskis total. And that was just to ensure that we would have some kind of detection. We threw in 3 more galaxies that didn't quite meet these criteria. And that's mainly because there were people in our group who had done work on them, and they were extremely interesting galaxies, which also showed some halo activity. Now, if you looked at the results, we ended up from our 35 galaxies with mixtures of all kinds of different types. There were AGN galaxies, there were H2 type and minor nuclei, various star formation rates, some interacting and some not. And the question then is, were there biases in the survey? Well, there can always be some, but if you look at our list of criteria, there aren't that many, we didn't actually choose the high star formation rates, for example. We did choose fluxes that we could detect. So that's the only possible bias by choosing L-band flux greater than 23 millijanskis. However, if you look at the star formation rates that we ended up with, they range from 0.02 to 7 solar masses per year. So we didn't actually choose high star formation rate galaxies, even though we had chosen this 23 millijanskis for our limit. The median galaxy star formation rate is about 1 solar mass per year. So basically, we're looking at Milky Way style galaxies. Before I go through the results, I just want to point out our website, our public website. It's very simple. It's queensu.ca/changes. And from here, you can just click on a galaxy and you can get a fixed download of our data, or images rather. If anybody is interested in working with, say, our UV data, you can certainly just send me a note, and I can talk to you about going through with that. So there's something in the chat, but I don't know what it is. Okay, so sorry, I wanted to go back here. So when you click on a galaxy, you can download D and B configuration data, both frequencies, total intensity, polarization. X means the vectors, magnetic field vectors, with and without primary beam correction. We also have H-alpha data you can download, H-alpha images, and polarization images from here. And one thing that is not there yet, which I will put up, is some H1 data, which we have from our Chinese colleagues. Okay, so let's move on here. So first of all, I'd like to now look at some results from total intensity. This goes back a few years, actually. This, I think, is a really beautiful edge-on galaxy. It's why we call the perfect edge-on galaxy. UGC 10-288. And previous to changes, this was what it looked like at publication. Excuse me. The previous radio image can be seen at the lower left. This is back in 1991. And so we wanted to see what we would find. So when we observed it changes, this is what we see. The pink here is actually an infrared image. What we see is this blue stuff. And you can see that there's a background quasar right behind this galaxy. Now, the background quasar in the original image down here at the lower left can just barely be seen as a little spike. But we could actually separate the radio emission from the background image, which wasn't done originally here. And we found that we had to revise our star formation rate downwards quite a bit for this galaxy, because the previous value had included the background source. And we also looked at the galaxy itself was only 4.4 millijanskis at 1.6 gigahertz. In other words, this galaxy fell below our original criterion for choosing galaxies. The reason I like to show this galaxy is because it was the first and only, by the way, galaxy in which we combined every single data set. So we combined the 2 data sets at L-band together with the three data sets at L-band together with the 2 data sets at C-band. And in fact, you can then throw it all together and you can create a new map which fits a spectral index to the whole thing, which point by point. And now we have images at 4 gigahertz. So we didn't actually observe at 4 gigahertz. We just have a gap between L-band and C-band. But by combining the 2 data sets and interpolating between them, we can get these results. The other point I wanted to make about this is that the galaxy itself, if you look at the bottom picture, it actually shows interesting structure above and below the plane. So even though we have a really low star formation rate galaxy here, we still see halo structures. Continuing with the total intensity results, some of them, here we see NGC 3556. These are all published, by the way, and the public website that I pointed to links to all of our papers. So if you wanted to go to that website, you can see, you can click on any of the papers, and this is one of them. Here we see 3556, Arpad Mishkolci combined our data set with some LOFAR data and shows these 2 images. The picture on the right shows the magnetic field, equipartition magnetic field strength in this galaxy. And as you can see, as you go up away from the plane, the magnetic field strength goes down a bit, but it doesn't go down to negligible values. We've got something like 4 microgauss, you know, 6 kiloparsecs above the plane. He fit the results with an accelerating wind and starting at about 125 kilometers per second in the plane and going to about 250 kilometers per second by a Z height of 6 kiloparsecs. So these are significant winds. Here's something similar done more recently, NGC 5775, which was the picture superimposed on the median that I showed you earlier by George Heald et al. And there's an archive number here. A lot of work was done here. It has a fairly high star formation rate, 7 solar masses per year. And on the right, we see a magnetic field mapped out again, equipartition. So in this case, if you go high above the plane, you're still getting something like 8 microgauss for your magnetic field strength. Again, an accelerating wind seems to fit the data the best with a 500 kilometers per second wind by a Z height of 6 kiloparsecs. So this, in fact, exceeds, we think, the escape velocity. So these really are winds that go away from our from the disk itself. In this particular case, the mass loss rate is something like 40 to 80% of the star formation rate. So these galaxies appear to be open boxes. In terms of the total intensity, I'm afraid I'm going to have go over time, so I don't want to do that. So I'm going to be just picking and choosing here. But Marita Krause looked at 13 of our galaxies and again applied winds from these systems, measured the scale heights. They tend to be of order 1 to 1.5 kiloparsecs for exponential scale heights. The magnetic field scale height is going to be about 4 times the synchrotron scale height. So that would suggest magnetic fields, something like 4 kiloparsecs for an exponential. An interesting result, I think, is that physically larger galaxies have physically larger scale heights. So it sounds obvious, but it's actually an argument for scalability, meaning if I just have a physically larger galaxy, it's going to have a physically larger scale heights. And it's an argument for my stacking earlier on where I scaled everything. So I think that we're sort of happy with the fact that that these galaxies do scale. Now, if, however, you correct for that, and if you create what we call a normalized scale height, in other words, I've now adjusted for the fact that larger galaxies have larger scale heights. And if I plot the normalized scale height, in fact, Marita, sorry, did, not me, if we plot the normalized scale height against the mass surface density going to the right, you can see that it declines. So this suggests that where a galaxy has a higher mass per kiloparsec squared, you've actually slowed down the wind in a sense. You've actually showing an effect of the surface gravity on those winds. What I'd like to do now is to move on to polarization. And the first result is NGC 2992. What you're seeing here is just an optical image of this galaxy. It's actually interacting. And the first image with contours here shows you the total intensity contours. Okay, so this is kind of messy, but nothing blows you away in terms of identifying this or that. You know, you've got the lowest contour where you've got some stuff sticking out. If you look, however, in polarization, this is what you see. And now you can see that there are two features on either side of the center. This galaxy does have an AGN. And so what we're saying is that in polarization, you're showing new features that you would not normally have seen from the intensity, total intensity. Here's another example. Here's this galaxy NG 3079 where we have GMRT data. The left image is the total intensity where you see the double lobe source. There's radio lobes on either side of an AGN in the middle. But on the right-hand side, this is the polarization, and the contrast between the polarized flux and the disk is very strong. The total emission is weaker than the left picture, but the contrast is greater. And so the polarization is uncovering hidden features that we wouldn't normally see. This is another example, NGC 5792. Here we see double-lobed radio structure on either side of the nucleus. That was completely masked if we were looking at the total intensity. Now, we're still looking at polarization. There's a lot going on here, and I'm not really going into details, but I rather like showing this picture simply because there's so much going on. There's so many features here. This is NGC 4388, which is in the Virgo cluster. And this is led by Ankor Damas Segovia, where he published the polarized results. But you can see the vectors here show the direction of the magnetic field which in the plane of the sky. And lots of, as you can see, he's named them filament this and blob that, and so on and so forth. Here, let's go back a bit. So this, by the way, is the contours on the right are total intensity contours. So now if we go to the next image, now we're looking only at the polarization. And I think the main point I want to make here is that the polarization looks, again, very different from total intensity and provides more information about what's actually going on physically. There's some magnetic field strengths here given to you in this slide. Okay, now, again, polarization. This is NGC 4631. I'm showing you, here's an optical image to the left. On the right, I'm showing you again the direction of the magnetic field with the vectors. And my point from this image is, this image, by the way, has not been corrected for a rotation measure. But what you do see is very sharp changes in the direction of the magnetic field. And there's a circle here, and I've circled a star-forming region. So where there's a star-forming region, it appears that this can be connected, this can be associated with very strong changes in the magnetic field direction. But I also want to point out that this is occurring on fairly small scales. So on local scales, our star formation regions seem to have a significant effect on the magnetic field orientation. So this is what I mean by local scales, maybe up to a couple hundred parsecs. Now, on the other hand, if you go to broad scale and you look at the broad scale emission, this picture here is not from changes. It was known sometime by Krause et al. And you can see a kind of X shape. Now we're talking kiloparsec scales. So you've got an X shape sort of going out this way and down that way. We find, however, from changes that these X-shaped fields seem to be ubiquitous. So if you look at the picture here on the right, this is NGC 4217, and the vectors, and you see this kind of shape down and out and so on. And what's more to the point is if you stack the images, it's still there. I actually want to emphasize this because I think it's a really important result from changes. We took 28 of our galaxies. I took 28 of the galaxies. Again, I scaled them to the same size, angular size, rotated them properly. But this time I went a little farther than the original total intensity weighting or stacking. I weighted them by RMS at every position. Then I took all the Qs and averaged them. You may have to, I'm not sure if you've gone through Q and use Stokes images, Stokes parameters, but I'm going to hope that that comes for you a little later. We took all the Qs and averaged them, then took all the Us and averaged them. And from those averages created the total intensity, the polarized image, which is the square root of Q squared plus U squared, as well as the angle, which I'm calling X here. Now, if galaxies had polarization structures that were all different from each other, you would expect a complete mess in the result. You'd expect the Qs to average to basically zero, that can be positive or negative. Same thing with the Us, and you wouldn't see anything. But what we do is we actually see something. So if you look in the right-hand pink picture here, you can see a sort of structure which is similar to the X-shaped fields that we see in individual galaxies. And I know some of you might be thinking, well, maybe there's one galaxy that's dominating everything else. But in fact, that's not true. If you look and scrutinize this in detail, it appears that this X-type structure is universal, if I can use that word maybe with a small u, for many spiral galaxies. So there's a dominant mode, which is X-type, and that X-type is kiloparsec scaled. Also, by the way, as you go up, the degree of polarization increases with Z height. So in fact, fields are becoming more ordered with height above the plane. I'm going to skip this one because of time. I'll come back to it if I need to. What I think is one of the most interesting results from changes is this result led by Karolina Mora Patierova on NGC 4631. Now, what she's done is careful rotation measure synthesis of this galaxy, which corrects for rotation measure at every point. The image that you see in the ground down here is total intensity contours, just so you get an idea where the galaxy is. And right in the middle, you see it's blanked, and that's because it's so Faraday thick that you don't see any polarization at all. However, above and below the plane, you do see polarized emission, and the vectors you see here are the direction of the magnetic field in the plane of the sky. Now, what are all these colors? I want you to take a look at the colors carefully, because if the colors are like blue and red, they are the rotation, the magnetic field is positive. And if they are grayscale, the magnetic field is negative. What does that mean? It means positive would be a component of the magnetic field along the line of sight is pointing towards you. And negative means that the component of the magnetic field along the line of sight is pointing away from you. So now we're going to go back to this image. Let's go a couple of kiloparsecs above the plane and go left. So now I'm going to go, we have a negative field. So the magnetic field is pointing away from you. Now the magnetic field is pointing towards you. Now the magnetic field is pointing away from you. Now it's pointing towards you. Now it's pointing away from you. Below the plane, it's not quite so obvious, but it still does a similar thing. Get magnetic field points towards you and away from you, and so on. This is completely unexpected. What we're seeing is a regular pattern of magnetic field in the line of sight, which is changing its direction significantly. Now, you might say, okay, this is a weird galaxy. There is some interaction with its other companion. Maybe something's happening there. But if you look at other galaxies in the changes sample, they all show similar features. 3044 is not interacting. It seems to be isolated. And it's got all kinds of changes in direction of the magnetic field. Remember, it's the component of the magnetic field, which is in the line of sight. And sometimes the data are hard. Their signal to noise is sometimes not great, but pretty much all the galaxies show something similar. What's going on? We see reversing rotation measures in the line of sight, but we also see structure of the magnetic field in the plane of the sky. It appears that there's some kind of cones or spirals going up into the halo in the magnetic field structure. In order to see this kind of thing, we can't really be talking about local features. We cannot be talking about just some, star-forming region in the disk, although it's important. We need some kind of broad-scale dynamo action. And so what patterns you see depend upon what modes in the dynamo may be dominant. So with Richard Henriksen, we've done some models, and I told Richard to be present. Richard, by the way, is my husband. I told him to be upstairs and ready in case there are difficult questions about this. So here we have the left-hand picture is a fit of various structures, bisymmetric, axisymmetric in the field. And if you look along the line of sight, you can actually reproduce this changing rotation measure. So we're fitting here NGC 4631. I'd like to point out a paper by Alex Woodfinden, who was our student. And if you put these structures, if you add them up in terms of what you would expect in a line of sight magnetic field, you can reproduce the changing rotation measures. So here we have fit to NGC 4631 with an outflowing union. You can see negative, positive, depending upon the structure of these fields. These fields are actually not necessarily confined to the plane. They come up on cones. So here's another example on the right, and here's just a quadrant showing you a changing rotation measure. And in this particular case, the vectors on the upper part show how the fields are changing, and it's just a slice, a vertical slice through a specific plane, and it's done well. You can't show in 3 dimensions so easily, but this particular image on the top is just a slice. Okay, what else? There are other options. We've looked at the other galaxies, which it's hard to do because the signal to noise in some cases is not very great, but for some of them you can see it quite well. And look at different cases. For example, a turbulent dynamo with accelerating wind plus a halo lag looks a certain way, and then we get a result of rotation measure as a result from that. This is actually still, there's a number of papers on this, but it's still, I think, in its infancy, and so a lot of work could still be done to try to understand how the halo structures compare with the magnetic dynamos that you're putting in. Okay, so let's do a summary here. Now, our conclusion from changes is that star formation related activity, say up to a few hundred parsecs, generates subscale turbulence, which is actually an ingredient in the dynamo. The star formation activity supplies, of course, the cosmic rays that are needed to illuminate the field, and they affect local magnetic field topology. However, winds from individual star formation rates can't explain global field patterns. Such patterns can be reproduced by magnetic dynamos, which are both fundamental and robust to local dynamics. You can, what I mean by that is, you can have all sorts of star formation activity going on in the disk. It's important for the dynamo, but the dynamo itself that generates these fields, and the fields tend to be fairly robust. All kinds of stuff can be going on in the disk below, but you get these large X-type fields anyway, and they seem not to care on the large scale. So dynamos on the large scale, depending on what models you're using, they can explain global reversing rotation measures. They can explain X-type fields in the sky, depending on the dominant mode. They can connect the disk to the halo regions in cones and spirals, and they can account for lagging halos. Scale invariant results show overall agreement with numerical work, and I'm just going to refer you to a paper here where we talk about that. Okay, what's next for changes? In changes, it has changes 2. It's being led by Volker Hiessen with Jelena Stein and Teresa Wiegert. And the idea here, well, it's not just an idea, we've actually got the data, is to fill in S-band. So if you can see the picture here, we have this gap at S-band, and we've now collected data for all galaxies at S-band. It was only done over the summer of 2021. So we barely have any images yet, but we want to be able to understand the cosmic ray, the spectral index of the cosmic rays, position by position in the disk and the halo if possible. And we'd like to know where things transition from what we call Faraday thin to Faraday thick. In other words, at C-band, the disk seems to be fairly thin in Faraday depth. But when you go to L-band, you start losing emission because you've gone to Faraday thick now instead of Faraday thin. I think I may have to let Dr. Sakia explain that separately. We'd like to know how fields connect from the disk through the halo and into the IGM. Where do the field lines close? They should close somewhere. I've got a little picture of a magnet here. Wouldn't that be great to see something like this on the largest scales? And what determines which magnetic field structures dominate for particular galaxies? That we're not even beginning to understand that. Just we are at the beginning, but not anywhere near where we'd like to be. So there's lots of room to do complementary studies for changes. For example, how about GMRT? It would be lovely to see a low frequency GMRT survey of the changes galaxies and extend what we have learned into the low energy cosmic rays. So I think I should stop there and allow for some questions and discussion. Thank you.
So you're welcome to unmute yourself and ask questions. I mean, just to help them understand a bit better. As they were asking questions in the chat, I kept answering, but now you can ask your questions directly to Professor Judith Irwin.
I see there's 28 in the chat. I still don't know how to look at the chat.
You can unmute yourself and ask.
Can I ask a question in the meantime?
Please, Desh, go ahead.
Yeah, so how would the structure of magnetic field would appear to an external observer in the light of what you have shown in terms of the, probably the alternating fields and connection to the halo in the Z direction. Has there been any investigation on that side?
I'm not sure what you mean. Are you talking about the Milky Way galaxy?
Yeah, the Milky Way.
Okay. Yeah, yes, there have actually been some studies. It's very hard in the Milky Way, of course, because of our location in it. However, if you look up Jennifer West, W-E-S-T, she's just recently published a study of the Milky Way and the reversing magnetic fields, and it appears that the Milky Way is doing the same thing. In fact, I think I might have.
Yeah, the reversals are well known within the plane. I wonder, does the structure continue at some large Zs?
Yeah, it does. I thought I had a picture. I'm just looking to see if I have a picture from Jennifer's paper. It doesn't look like I do. But yes, in fact, just recently, her paper, Civica West 2021, I think, she's looked at the way that the magnetic fields in the Milky Way reverse going up into the halo in the same way that I'm showing you here. And she's looked at, she's used the model, the same model, the Henriksen model, to see if she can make it fit. The thing that confuses me a bit is when you look at different galaxies, you look at 4631, for example, you see all those changes in, back up. You see, going up again. Yeah, you see, all this change one to the other. Now you go to a different kind of galaxy, and I don't have them all here, but they don't do exactly the same thing. And so you have different modes dominating and so on. And I looked through all the galaxies to see if there was a pattern that matched the Milky Way, because it looks like there's a certain structure. I think it's plus minus on one side and minus plus on the other as you go above and below the plane of the Milky Way. And I only found one galaxy that seemed to be similar, but the signal to noise was really low in that galaxy. So then the question is, what determines which mode dominates? What determines why the Milky Way has plus and minus above and below the plane on one side, minus plus on the other side? So that means a certain mode is dominating, but you don't see that, say, in 4631. So what is the deciding factor? And I don't know what that would be.
Yeah, thanks. Does the scale of this match with the sort of in the cases of spiral arms, spiral galaxies, the number of arms and the number of reversals?
The scale matching Milky Way? Well, globally, yes. I mean, these are all basically like the Milky Way in size and star formation rate.
Like the inter-arm spacings and.
Yeah, you can't really tell from these edge-on galaxies. I think you'd have to look at a face-on to try and study the spiral structure. So it's kind of hard to tell from what we have.
Yeah. Probably intermediate inclination would do better, right?
Yeah, maybe. Maybe it would be. From models, you could actually, this is something we haven't done yet, but probably should, start with the models and then map them all, like turn everything so it's face on, and then say, is there any way that by going face on, you can tell something that you couldn't tell, edge on, this kind of thing, and see if we can match them up that way. But nobody's done that yet.
Yeah, thank you very much.